This brings us to our momentum lens and how vector components can be used with momentum. In the next hour, we'll deal with kinematics. We know that if an object is moving in this direction and it collides with another object that was at rest and they stick together, the two objects will continue moving in that direction, stuck together. And if we have an object moving in this direction and it collides with a stationary object, the two objects stuck together will continue moving in that direction. So it should be no surprise that if we have one object moving in this direction and one object moving in this direction, and they collide and stick together, and let's pretend that they're about the same mass and they're about the same velocity, where would they end up? We know if these two objects stick together, there's going to be some momentum to the right and some momentum towards the top of the page. The velocity will point somewhere in the direction between C and F. Momentum conservation is a vector equation. Initial momentum equals final momentum when the net force on our system is zero. If there are multiple objects in our system, then this is a sum. The sum of all the momentum at the beginning has to equal the vector sum of all the momentum at the end. So we don't have to break up momentum into components. We can add momentum. If we have our two objects in the previous example, mass 1, velocity 1, initial, mass 2, velocity 2, initial, we could add them up. We have a momentum from object 1 that points in this direction. We have a momentum from object 2 that points in this direction. We add them up to get the red vector here, the sum of the two, and that's the initial momentum of our system of two masses. So after they collide and stick together, they have to have the same momentum they had initially, so the two have to go off in that direction. Of course, this is only true if the momenta are approximately equal at the beginning. What happens if I make the momentum of object 2 much bigger? Let's make it 10 times bigger by keeping the velocity the same and making it much, much more massive. What direction will the final momentum be now? It's going to be somewhere probably between C and D. Object 2 is going to dictate the direction much more than object 1, but we still have to have some momentum to the right because mass 1 had some momentum to the right before the collision. As I just showed, we can treat momentum as a vector and add it as a vector, but we can also do it as components. Here I have two masses. Maybe they're billiard balls. You're shooting pool. And M1 comes along and it strikes M2 a little bit off center. Well, what happens? M2 goes off in this direction. And M1 goes off in this direction. And what do we know? We know that the momentum initial has to equal the momentum final, because there are no external forces acting on our system. So one way to deal with this is to use components. If the momentum is the same before and afterwards, then the momentum in the x direction has to be the same, and the momentum in the y direction has to be the same before and after the collision. So in my example here, I have all the x momentum is in mass 1 initially. Nothing is in mass 2. And at the end, I have to take the components here. V1 final x component is V1 final times the cosine of theta 1 and this gives me one equation, and I can use the y components to get a second equation, and I can use these two equations to solve for two unknowns. So in the y direction, I know I started out with 0 y momentum. Neither one of these was moving in the y direction initially. So that means I have to end up with 0 at the end. This one is going to have positive y momentum if I call towards the top of the page my positive direction, and the other one is going to have negative momentum in the y direction. And those are my two equations, and I can solve for two unknowns given everything else in the problem.